Hello. So what I'm going to be presenting on is this sum up here. So I'm going to be presenting on finding the sum from 1 to infinity of -1 to the n over n to the fourth using the residue theorem. There's a whole bunch of details on page 142, so I'm pretty much going step by step of exactly what the book is suggesting to do. The only difference is that there's z to the fourth and there's an alternating sum. So let's just jump into it. So first, the book considers says to consider f of z is equal to pi over z to the fourth times sine of pi z, as other people have done in their projects. I don't know where this came from. Dr. Covert said that this is possibly just the logarithmic derivative of something that's also important. That part I can't explain, but that was one of his replies. So our first thing to do here is to calculate the residue of this function, right? So I'm going to do this in two different kind of steps. The first in blue, which is going to be the residue at 0, and then the second in like that goldish tint color, which is going to be the residue at each integer 1, 2, 3, and -1, 2, 3, and so on. All right. So I'm going to start with just saying that there are different poles, right? So we can have the denominator equal to 0, right? And that's only true when z to the fourth is 0, so z is 0. All right, our other option is sine of pi z is equal to 0, so pi z is equal to 0, pi z is equal to 1, 2, 3, and then also all the negatives. So our residue of the entire function is going to be the residue at 0, i.e. the residue in blue, and the sum of the residues in gold, which I'll explain here in just a minute, right? So I think the easiest place to start on this is the residue in blue, i.e. the residue at 0, okay? And to do this, I found that the easiest way and the most direct way to do this was to use the Laurent series, okay? So the Laurent series for pi over z to the fourth times sine of pi z, I just centered this at 0, so I took out the pi over z to the fourth, and then I had the Laurent series for 1 over sine of pi z, which ends up being this in parentheses. So 1 over pi z plus pi z over 6 plus 7 pi cubed z cubed over 360 plus, etc. Okay. And when you multiply that pi over z to the fourth times all of that, right, we get 1 over z to the fifth plus pi squared over 6z cubed, and then 7 pi to the fourth over 360 times z. And this is the one that we're worried about, right? This is the z to the -1 term, which is the residue, right? So in this case, the residue of f of z at 0 is going to be 7 pi to the fourth over 360. Okay, so we're just going to leave that there for now. That's important, and we'll come back to that here in a second. The next part, which is a little bit trickier, because this is a little bit more outside of what we've done, maybe not entirely, but a little bit. I found it hard, just put it that way, is the residue of f of z when sine of pi z is equal to 0. Okay, and this is trickier because there's an infinite amount of them, and we need the sum of all those, right? So what I use is, right, this definition, right? So the residue of f of z is going to be some g of z over h prime of z, okay? So if we just let g of z equal pi over z to the fourth and h of z equal sine of pi z, right, if we plug it into that formula, we get 1 over z to the fourth times cosine of pi z. So we're right here. Okay, and this is going to act like a certain sum, okay? So for z in the integers, and I didn't actually mean to say that, but for n in integers, cosine of pi z is going to act a whole lot like this alternating function, right? So -1 to the n minus 1, it's going to act a whole lot like that. So then 1 over z to the fourth times cosine of pi z is going to act a whole lot like -1 to the n minus 1, or just to the n, over n to the fourth, right? Z is going to act a whole lot like n to the fourth. Z to the fourth is going to act like n to the fourth. 1 over cosine of pi z is going to act like negative 1 to the n, right? So that's going to alternate between negative 1 and 1. So this residue is ultimately just going to be the sum from 1 to infinity of negative 1 to the n over n to the fourth. Okay, at least that was my logic behind it. So that's all the positive integers. And then we can do the same thing for the negative integers. We can just pop a negative on in front of that n, and everything just about ends up being the same. So I didn't really mean this. I just meant to plug in n is negative. Okay, so again, that acts the same thing. 1 over z to the fourth times cosine of pi z. That's going to act a whole lot like negative 1 to the n over negative n to the fourth, which, because of that that fourth power, right, this is just going to be negative 1 to the n over just n to the fourth. Okay. So these residues, right, for every n, we're going to have a residue at that n. And that's going to be the sum from n equals 1 to infinity of negative 1 to the n over n to the fourth. And there's going to be two of them because we have n is equal to 1, 2, 3, right, all the positive integers. And then n is equal to negative 1, negative 2, negative 3, all the negative integers, right? So we have those residues at the integers, and then we have the residue at 0. Okay, so we have a couple different things. We have that residue in blue, we have the residue for n is positive, and then we have the residue for n is negative. And we're adding up all those things together, and that's going to give us our integral of f, and then we'll go from there. Okay. The second thing the book has me do, is to consider this gamma, right? And this gamma is going to be the rectangle from n plus 1/2 minus in up to n plus 1/2 plus in over to negative n minus 1/2 plus in, and then down to negative n minus 1/2 minus n, and then back. Okay, and within this, we're going to have a set number of, or an unlimited number, I guess, if n goes to infinity, of these residues, these poles, right? So we have the 0, so that's going to be in the center in blue, and then we have each of these n equals 1, n equals 2, and n equals any integer. Okay, so that's what we're going to be trying to do. We're going to try and find this integral within this gamma, and then we're going to try and use those residues to do that. Okay, so then next, we have to, in order to like take our integral over this gamma, we've got to limit our function, not limit, bound our function. That's the word I'm looking for. So we have this identity, right? Secant squared is equal to 1 plus cotangent squared. We know that. In another exercise that I think Jacob did, it says that the absolute value of cotangent of pi z, that's going to be less than 2, right? So I'm right over here. So if we square that, it's going to be less than 4. Add 1 to that, we get 1 plus cotangent squared is going to be less than 5. So therefore, 1 over sine squared is going to be less than 5, and 1 over just sine is going to be less than the square root of 5. So that bounds our function, which is going to help us in taking this overall integral. Okay, and then that part B says to find the limit as n approaches infinity of the integral of that over gamma n of f, which is going to be the limit as n approaches infinity of the integral of gamma n of pi over z to the fourth sine of pi z dz. Now, because we bounded that function, we know that the max value of 1 over sine of pi z, that's just going to be equal to rad 5. And then we can also bring that pi out. That's how integrals work. We can take those constants out. So we're just left with the integral of gamma of 1 over z to the fourth. And if we take that integral, we get pi rad 5 of z to the negative 3 over negative 3, which we're taking the limit. We're evaluating from positive infinity to negative infinity, very basically. That's not exactly what you're doing, but that's what's happening. Okay, and when we do that, this distance z ends up going to infinity, so this entire integral goes to 0. Okay, we can also look at the graph. The graph ends up being just a whole bunch of, essentially being a whole bunch of boxes really, really pushed together. So we could even see that that area is almost going to 0. Okay, so putting things together, right? So this is the last little bit. our formula says that the integral over that gamma is going to be equal to the sum of the residues. Okay, and one of those, like the gold residue, is the one we're really looking for, and we have the other two. So the part in pink, that integral, that's going to be equal to 0. The part in blue, that residue at 0, is 7 pi to the 4th over 360. And then we had two sums from n equals 1 to infinity of negative 1 to the power of n over n to the 4th. All right, so if we just solve for this, we're going to have our identity. We're going to have our summation, right? So if we just subtract over the negative 7 pi to the 4th over 360, or sorry, the positive, which becomes negative, and then divide by 2, we get that the sum from n is equal to 1 to infinity of negative 1 to the n over n to the 4th, which is going to be equal to negative 7 pi over to the 4th over 720, which I checked. I don't know if I actually said this at the beginning of the video. I checked on Wolfram Alpha, and that is exactly what I got. So that is the work in the nutshell. So I hope this makes sense. All right. Thank you.